Alright, so today's question is 426. Convert binary search tree to sorted doubly linked list. We've been given a binary search tree. We need to convert that tree into a sorted circular doubly linked list in place. We can think of the left and right pointers as synonymous to the predecessor and successor pointers in a doubly linked list. And a circular doubly linked list, for a doubly linked list to be a circular one, the predecessor of the first element is the last element, and the successor of the last element is the first element. So basically, based on the example graph here, this is a binary search tree, and we need to convert that into a doubly linked list. For it to be a circular one, the last node, it's a successor pointer, or in the if we just we pretty much have to reuse the linked tree node definition here. So the right pointer of the node with value 5 is going to pointing to the node with value 1, and the left pointer of node 1, node with value 1, is going to pointing to the node with value 5. So for the algorithm to be in place, we're not gonna making any new nodes. All we can do is changing the left and right pointers. And what else here? You can think of left and right as synonymous to, and the transformation is in place. In the end, we should return the pointer to the smallest element of the linked list. So if we're initializing some kind of a dummy reference here, like a head node, with one of the pointers pointing to the node with the smallest value, in the end we just return the reference of that pointer. So there's more explanation. The graph shows how the transformation is done. Okay. So the dotted line is the predecessor, and the solid line arrow is the successor. I don't know, it seems to be very complicated, this graph, but anyway, the based on the property of binary search tree, if we do the what order it is, it's left, node, right, so it's in order traversal. If we do in order traversal, we would extracting values of the nodes that's in sorted order. So basically we just have two pointers. One is for the current traversing node, one is for the previous node, and we just do in order traversal and changing the references of the previous node and the current traversal node. And we're always pointing the left pointers of the current traversal node back to the previous one, and also update the right pointer of the previous node to the current traversal node. After that, we just dealing with this head node a little bit, as well as the in the beginning we deal with this head node reference to the smallest node in the beginning, and after the traversal we deal with the circular reference handling, and that will be just be the algorithm. It will be the linear time in time complexity, because we just do in order traversal, and the space complexity is constant. We just have a few reference pointers. So yeah, in short, this just doing we just do in order traversal and handling the changing of the swapping of those reference along the way. So pretty straightforward actually. There's no complication or anything. It's just I guess it's just testing whether you can you know how to do in order traversal. So let's code this solution up. Are we guaranteed to have a root node? No value restriction here, and this is for the binary search trees property. All values of this are unique, and number of nodes can be 0, so there could be this edge case. So if not, we just handle this edge case first. If there is no node, we just return it, and otherwise we just do in-order traversal. We'll have a stack and a traversal node, which initializing to be initially it's the root node, and let me just code the iterative version of in-order traversal first, and after that I will add in the code to handling the swapping of these references, as well as dealing with the having a head node pointing to the first one, as well as dealing with this circular references. So while we have node to traversal, or we have some node on the stack, what we would do is to try to go to the left. This time I would try to not block the example here. So we would try always, when we have a node that we need to explore, we always try to go to the leftmost children of it. So that's while we have a node to work with, we put that node onto the stack so we can backtrack to it. And we'll do traversal node is left. So example here, when we see node 4, we put that onto the stack to remember that we need to come back to it, and we go to the left one, and this is still a valid node, so we put that onto the append that to the stack, saying that we will definitely gonna return and check on this node, and then go to the left because it's a leaf node. After this while loop is gonna break. After the while loop is break, we popping the node from the stack. So this one will be the node 1 is gonna be the first node that's gonna actually popping out of our stack. We will do some work to it, right? So after we perform some work on this first node here, we'll backtrack to the node here, and after we do some work to this node, we'll actually try to explore the right node. So that's with this line here. And in the end, we need to return the head node here, which has a right pointer pointing to our initializing, the first node in the doubly linked list. So for this to work, we have to link the head node to the first time that we see we're popping out of the node from the stack. So let's initializing the head to be a empty node here, and if we haven't linked the head node yet, so the reason why this works is that this line is going to only execute once, and the first node that's popping out of our stack is is this node. So this line here is gonna establish this reference link here. Sorry, it's gonna establish this link. It's guaranteed to be the case. And for the purpose of establish these predecessor and successor links, we also have to have another node to keep track of the previous node in the traversal order, so that when we traversal to node 2, we have a reference to node 1, so that we can change their right and left pointers to pointing to each other. So for that reason, we were also initializing the previous pointer to be none in the beginning, because the it could be some dummy node, but I guess none works better. So let's say now our previous node is node 1 here, and the current node, the traversal node, is node 2. What we would do is to basically saying that the previous nodes, the right pointer is going to pointing to the traversal node, and the traversal node's left pointer is going to pointing to this previous node. So yeah, basically to establish this predecessor and successor links. And since that in this line we are advancing to the next node in the in-order traversal order, we keep track of this. We basically keep a reference of the previous node here. So that's pretty much the logic of dealing with this in-between nodes predecessor and successor reference. This line here dealing with the head node pointing to here, but it doesn't solve this circular links here. That's something we handle while we finish the in-order traversal. And because the head node is have a right pointer pointing to the first node in the doubly linked list, and after the traversal node is this very last node here. So the relationship become very clear. That's the is that right? Let me think about it. Oh yeah, because the traversal node is advancing to the right, so actually after the while loop, this previous reference is gonna be the last node in the doubly linked list. So that's we change the right pointer of that to be the first node, and we change the first node's left pointer to become to be this previous node, and that will these two lines will solve the circular links. Make circular. So this is PRED links. This is grab a reference to the first node. Yeah, that's pretty much the code for this problem. Oh, so yeah, so I guess the space analysis is wrong. We're having a stack here, so it depends on the structure of the tree. If it's a perfectly balanced binary search tree, the space we need for this stack it's log n. But if it's a degraded tree, like if it's initially, if it's degraded to a linked list, a single linked list initially, with this stack will be order of n. So yeah, for space, I'm sorry. The time complexity is order of n because we're doing in-order traversal, but the space is log n in the best case and log n order n on in the in the worst case, O log n in the best case. So I'm sorry about my mistake. So I think it should, this code looks right to me. Let me submit it. Okay, it works. So this is a problem for today.